The wheel is considered the greatest invention of all time. That is one invention from where it all began. All the modes of our daily transportation such as bicycle, scooter, car, bus, train and even airplanes need wheels. The wheel functions as a turbine in engines and machines to lend them mechanical advantage. Now, let me throw you a rather frequently asked question. How do cars move? The tires of the car push on the road. The friction between the road and the tire propels the car forward. Movement of a train has a similar story, where the friction between the track and the wheel causes the train to move forward. Now what about planes? Keep the newer versions of planes aside for a while. Let's consider the Wright brothers model. It had a propeller that pushed on the air to make their plane move forward. What about rockets then? A rocket in space has nothing to do with or nothing to push against. So friction is out of the picture. How else do you think it moves? Imagine a rocket which is very far in the outer space and not close to any other mass. This means that the rocket is not under the influence of any gravitational force. This rocket has to move forward somehow. Is it possible? A rocket carries with it the fuel and oxidizers needed for combustion. Initially, the rocket is at rest. So is the fuel inside the rocket. Let the mass of the rocket be m, that is the capital M, and that of the fuel be small m. What is the initial momentum of this rocket fuel system? The combined mass of the rocket and fuel is taken as capital M plus small m. The initial momentum of this system is P initial or initial momentum is equal to m plus m into 0, that is capital M plus small m into 0, which is equal to 0 kilogram meter per second. Now, inside the combustion chamber of the rocket, the fuel gets ignited and the mass is spit out from the tail end of the rocket with a velocity Vf or velocity of fuel. This causes the rocket to move with a velocity Vf, that is the rocket velocity. The reason why the rocket moves forward is the result of an important property of the universe called conservation of linear momentum. Let us analyze the final momentum of the system. That is Pf is equal to mvf of rocket plus mvf of fuel. According to the law of conservation of linear momentum, the total momentum of an isolated system of interacting particles is conserved. This means that the initial momentum of the system will be equal to the final momentum of the system. So, Pi is equal to Pf, which implies 0 is equal to mv of rocket plus mv of fuel. That is, Vf of rocket is equal to mv of fuel by mass. The negative sign indicates that the rocket will move in a direction opposite to the direction of the ejected mass. Here, we have made a very crucial assumption. That is, the rocket is far from the vicinity of any other mass. This means that no force, not even gravitational force, is acting on the system, meaning the system is isolated. In an isolated system, mutual forces between pairs of particles in the system can cause momentum change in individual particles. But since the mutual forces for each pair are equal and opposite, the momentum changes cancel in pairs and the total momentum remains unchanged. Collision is a great example of application of law of conservation of momentum. Consider two bodies A and B with initial momenta Pa and Pb respectively. They collide and gets apart with final momenta Pa dash and Pb dash. Now, applying Newton's second law of motion to the system before collision, we get Fab delta t is equal to Pa dash minus Pa. Similarly, after collision, Fba delta t is equal to Pb dash minus Pb. But according to the third law of motion, Fab is equal to minus Fba. This implies that Pa dash minus Pa is equal to minus of Pb dash minus Pb. Again, PA plus PB is equal to PA dash plus PB dash. That is, initial and final momenta are equal. Thus, we can say that the total momentum of the system is conserved in a collision, be it elastic or inelastic. We know that an object will be at rest if there is no force acting on it, according to the law of inertia. Imagine a condition where an object remains at rest even though several forces are acting on it. How is it possible? Does this violate the first law? Let's see. Now, let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.